Okay, let's dive right into this. Welcome to part one of today's explainer, where we're doing something I find absolutely fascinating. We're taking medium voltage, or MV, transformers, and we're going to unpack them completely, literally from the outside in. You know, we walk past these quiet metal boxes every day without a second thought, but inside, there is an incredible world of physics, geometry, and high-stakes engineering just quietly working to keep the lights on.
Here's our roadmap for this explainer. We're going to hit operating environments, mechanical features, magnetic core physics, and finally, winding geometry. So let's just jump right in.
Starting off with Section 1, Operating Environments.
You know, the golden rule of transformer engineering is actually pretty simple. If you put the wrong transformer in the wrong place, it's going to fail in month 6 instead of year 20. Seriously. So, how do we actually choose? Well, on one side, you've got oil-immersed transformers. These use a fully sealed tank where oil, either mineral or synthetic ester, acts as both an incredible insulator and a coolant. And because of that, they have a really compact footprint. The catch? Oil is combustible. On the flip side, we have dry-type resin-encapsulated transformers. These use solid epoxy resin and just regular ambient air to cool down. They're definitely bulkier, but they are fire-safe, which makes them the go-to for indoor setups. Also, oil units can go about 15 years between major samples, while dry types usually need visual and thermal scans every single quarter.
I like to think of it this way. Oil is kind of like a thermos. It's completely sealed, hiding all this quiet work inside. But if something goes sideways, the failure can be violently explosive. Luckily, the oil actually gives us an early warning through dissolved gas analysis way before things go boom. Resin, though? Resin is like an ice block. You can see right through to the coils, but the failures are silent. If extreme humidity or thermal cycling causes that hidden damage to crack the resin, well, it cracks fast, and by then, it's totally game over.
Okay, let's test this out really quick. Imagine you're designing an offshore wind topside module. It's completely unmanned, and it's just constantly getting battered by harsh, wet salt spray. Which of those two transformer types are you going to specify?
If you said the oil-immersed sealed tank, you nailed it. Think about it. Because the platform is unmanned, the fire risk to personnel is practically zero. But more importantly, that relentless salt spray means you absolutely need a fully sealed system to prevent rapid corrosion. If you stuck a dry-type resin transformer out there, that humid, salty marine air would eat it alive and crack it way faster than you'd expect. Plus, the oil's efficient cooling gives you a much more compact footprint, and offshore space is premium real estate.
Moving right along to Section 2, Mechanical Features.
So the nameplate on the front might tell you the electrical rating, but the mechanical fittings, kind of like the dashboard of a car, are what actually keep the thing alive. The most obvious features on an oil-immersed unit are those big detachable radiators, and they run on this brilliantly simple physics principle called thermosiphon cooling. Basically, hot oil naturally rises from the core and windings, flows outward into the radiator fins where the outside air cools it down, and then that denser, cooler oil just naturally sinks right back into the tank. It's a continuous loop of removing heat, and it does all of this without a single mechanical pump that could break down on you. Pretty elegant, right?
Next up, we have the tap changer. And this brilliantly illustrates how we manage fluctuating voltages on the grid. Think of tap changers as, well, basically bicycle gears for voltage. They aren't changing how hard the transformer is working, they're just adjusting the turns ratio in discrete little steps to keep your output voltage exactly where it needs to be. Oil-immersed units usually give you about 7 adjustment steps, which is great for handling those wider voltage swings you see on long feeder lines. Dry-type units, on the other hand, are usually sitting much closer to the power source, so they typically only need about 5 steps.
But dealing with these bicycle gears comes with a massive, massive caveat. Here is a critical safety question for you. Can you safely operate an off-load tap changer while the transformer is actually energized and pushing a load? Take a second and really think about that one.
The answer is an absolute definitive no. Seriously, do not do it. Offload tap changers physically reconnect the winding taps. If you try to switch gears while that system is energized, you're going to draw a massive, incredibly violent electrical arc. It'll instantly cause severe contact damage, or honestly, much worse. These things are designed for de-energized adjustments only. Zero exceptions.
All right, let's get into Section 3, Magnetic Core Physics.
So we've bypassed the external hardware, and now we're diving deep into the invisible physics happening right inside that iron core. A transformer's magnetic core is what actually links the primary and secondary sides together, entirely without a physical electrical connection. It's basically magic. But that magic isn't free. It creates what we call core losses. Core loss is essentially the sum of two things: hysteresis loss and eddy current loss. Think of hysteresis like, when you take a paperclip and bend it back and forth really fast and it gets super hot. That's what's happening here. Heat is generated just from realigning the magnetic domains 50 or 60 times a second. Then you've got eddy currents, which are these circulating currents trapped directly in the steel. To fight this, engineers don't use just a solid block of iron. Instead, they stack thousands of super thin, individually coated steel laminations, kind of like the pages of a really heavy book.
And this brings us to a really crucial, often totally overlooked paradox in power engineering. An idle transformer burns power just by magnetizing its own core. Literally, the exact second you close the breaker and energize it, you start paying for core losses. So zero load connected to the building absolutely does not equal zero loss at the transformer.
Let's put a real number on that so you can see what I mean. 17,500. A standard 1,000 kVA transformer that is just 2,000 watts of no-load core loss will waste roughly 17,500 kilowatt-hours a year, doing absolutely nothing but sitting there energized. Multiply that wasted energy over a typical 20-year lifespan, the cost of that invisible heat can easily end up being more than the original purchase price of the transformer itself. Wild, right?
So, if core loss is so incredibly expensive over time, it begs the question, why don't engineers just design every single core at a really low magnetic flux density and cut those losses down to almost zero?
Well, because physics demands a direct trade-off. Lower flux density means the magnetic field is way more spread out, and that means you need significantly more iron to carry it. If you try to design for ultra-low core loss, you end up with a much bigger, much heavier, and vastly more expensive physical core. It's a constant balancing act between upfront material costs and decades of long-term energy efficiency.
And finally, Section 4, Winding Geometry. Let's wrap some copper around that iron core and look at the secret geometry of how these windings behave. Windings generally come in two main flavors. You've got Y, which is shaped like a star, and delta, which is a closed triangle loop. Y is fantastic because it provides a neutral point, which is totally essential for handling unbalanced loads in a facility. Delta, on the other hand, is great because it traps harmonic distortions inside that loop before they can leak back out onto the utility grid. And the cool part? By pairing them together, like say a delta primary and a Y secondary, you very cleverly get the benefits of both.
Now, what's really interesting about this inrush current multiplier is a design secret hiding inside that geometry. When you first energize a transformer, the core briefly saturates and it pulls a huge spike of power called inrush current. But here's the crazy part. The physical placement of the windings completely dictates the size of that spike. Usually, the low voltage winding is placed on the inside, right up against the core. The high voltage winding is then wrapped around the outside.
So let's lock this concept in with one last check. If you have a single transformer sitting out there in a substation, does the inrush current multiplier stay the same regardless of which side you close the breaker onto first?
Nope. It behaves entirely differently. Because the inner winding sits in a zone of lower air core reactance, energizing from the inside out causes this violent inrush current that can spike 10 to 20 times the rated current. But if you energize that exact same transformer from the outer winding, the higher air core reactance actually chokes the spike, limiting it to maybe 5 to 10 times the rated current. Same transformer, same nameplate, but a totally different behavior on the grid, based purely on geometric placement.
So the next time you walk past a substation and you hear that steady, low-frequency hum, just remember what you're actually listening to. You are hearing magnetic domains in the steel realigning themselves 60 times a second. You're hearing invisible energy being burned, and you've got to ask yourself, how much is that costing right now? Thank you so much for joining this explainer, and we will catch you next time.